Hey folks, today I'm going to be talking about public key cryptography, in particular the RSA system. But I wanted to start off by giving you a sort of an analogy to think about public key crypto in terms of. So imagine you have the sort of strange mailbox that I've portrayed here. It has up at the top, there's a slot through which you can stick envelopes, but the slot is locked. It's got a flap that won't move. And there's a combination thing here, so like a combination lock, like you did on your locker in high school. So you turn it to the left 3 times, and then you set a number, and then you turn it back once. I don't know. There's a combination though for that. And then down here, there's a nice big open door that I can open up and get in and get all the letters out. And that's also got a combination lock. So far, so good. The thing is, the weirdness is this. I make that piece of information public. That is, I tell everybody what the combination is. Can't spell. I tell them what the combination is. So if somebody wants to send me a letter, they can go over here, dial in the combination, and stick their letter through the slot, and now it's in my box. Okay. But this combination I keep private. You have to make sure you tell no one about that one. If you tell somebody else what that is, you've ruined the whole idea. But the point of this funky mailbox is that it gives me a way to get secret messages sent to me. Anyone in the world can access this public information and drop a letter in this box. And then once it's dropped in there, nobody else can get to it but me, because I've got the combination for this thing, which is where you actually can get in and retrieve the letters. What I've just described there is a sort of physical manifestation of a thing called an asymmetric key system. One key that's public that allows for, well, might as well start saying it. We allow for encoding using a public key, but we only can decode if we have a private key. So if you could implement something like this, where there's this public combination that lets people send you a message, but there's a private combination that lets you retrieve the messages, we'd be set. The problem is to do this, without a physical thing around, but to do it with math. So how can we do this sort of thing with mathematics? The essential tool we use is something called a trapdoor function. And there's a whole bunch of different trapdoor functions in the world now. We're going to look at one of them today, but the basic idea of a trapdoor function is more general than the one example we're going to look at. So let's take a look at what we mean by a trapdoor function. It's a function that should be easy to compute. So think of it as f of x, right? A function. F of x is easy to compute. but the inverse function, f inverse of x, is hard. That's the essential idea. If you want something that in one direction, no problem, you just do it. In the other direction, wow, I don't even know how to get started. Ideally, it's really hard. But the difference in easiness and hardness is sort of tough. So let me give you an example, or sort of the example for today, of a trapdoor process. If I have two big numbers and I want to multiply them, it really isn't hard. It may seem like it's hard. Like if I presented you as individuals with two 7-digit numbers and asked you to multiply them, you'd be like, what? No, I'm not going to do that, because it would seem really hard. But seriously, you could get on a calculator and get it done. And in fact, multiplying, it actually can be done rapidly, even when the numbers involved are really gigantic. Multiplying. So what we're going to actually do is think about multiplying two large prime numbers. So you have a prime p and a prime q, and you multiply them together and you get their product. We typically call that n. So you may think, if p and q have hundreds of digits, this might take a little while. But in truth, it honestly doesn't. You get finished in microseconds. On a good computer, multiplying two things that have 200 digits each, well, it's done in the blink of an eye. Surprising, I think. But trying to reverse that process, not so easy. Factoring n I should have said the word easy here, because factoring in is the opposite. When you have just the product and you don't know what the p and q are, finding out what the p and q are seems to be really, really difficult. I said seems to be because that's still an open question, but it hasn't been proved that factoring in is ridiculously difficult, but it seems to be the case that factoring in is hard. So I mentioned the name RSA up here, and you see how it's got dots after it. That's an abbreviation for people's names. Rivest, Shamir, and Alman. So that company, which is, according to the book, is now owned by somebody else, but RSA Company Incorporated, they pose challenges to the cryptographic world. So it's kind of an interesting thing to look into if you want to do. Maybe somebody's project could involve looking up some of the RSA challenges. But basically what these challenges amount to is giving people n's and seeing if they can factor it. So let's think about some typical times for these things. Multiplying, that's about 1 millisecond, say. It could be a millisecond. It could be much faster than that on a good machine, but a millisecond includes some allowance for transmission delays while it's getting across the internet, that kind of thing. What about factoring? Well, for one of these RSA challenge problems, the expected time to factor the number is longer than the Earth will be around. I mean, it's kind of, insane. It's like 7 billion years. So that's a big mathematical challenge, isn't it? If using standard technology and the standard algorithms we have for factoring, you can estimate that the factorization should take 7 billion years. If you get that down to the point where you can actually do it in, a day or two, or even many, many months, well, that's a good thing. No, I'm actually just lying right now. I don't know that the 7 billion years is one of their challenge problems, but I know that any particular length of time you name can be achieved. You just make the primes involved bigger. So, right now people typically use 2 to 400 digit prime numbers, and then they multiply them together and they get a 4 to 800 digit composite number. And so factoring something with 800 digits, it might take 50 years right now. But if you just up the ante and make these be 1,000 digit prime numbers, then you've made it, wow, I don't know how many times harder, a lot harder. So getting it up to 7 billion years is quite conceivable. There's a trade-off that actually people make when they're coming up with these RSA type problems, which for now we'll just think of it as factoring, which is how long does a secret really last? How important is it that the thing we're encoding remains secret so that nobody will ever know it? Do I need it to last for the entire length of time before the sun grows into a red giant and swallows up the earth? Probably not. Do I need it to last, to remain secret for the lifetime of the individual involved? Maybe that. Would it be good enough if it was secret for the next year? Well, if it's that case, then you can use relatively small as P and Q. If you want it to last a lifetime, then larger P and Qs. So the degree of secrecy you want to create should inform your choice of how big the primes are. Because, it is going to be a little bit it becomes more difficult to multiply things when they've got 10,000 digits than when they only have 200. So you don't want to go outrageous if you don't have to. Plus, honestly, the key size gets pretty ridiculous. If you've got things with 10,000 digits in them, when you multiply them, you've got 20,000 digits. A 20,000 digit number is going to take up a lot of space. How are you going to write that down? How are you going to phone a friend and tell them what it is? Obviously not in spoken language. A 20,000 digit number would take you, probably most of the rest of your life to speak. So you don't want to do that. Anyway, I'm just trying to give you a hint of some of the considerations people have in mind when they go to do true public key systems. They don't necessarily need to make them, impossible to break for forever, but make them reasonably secure for the near term. Anyway. All right, so I guess that's a good enough of an intro to the sort of ideas we've talked about. You've got the main things are asymmetric key systems, where you've got a public key for encoding information, kind of turning it into something that's undecipherable, and then a private key which takes that undecipherable thing and renders it back into plain text. And then the idea of a trapdoor function, something that's easy to do in one direction but hard to do in the other. Ideally with a big difference between the easy and the hard. Multiplying and factoring are a pair of processes that are like that. All right, so let's actually do RSA. Leaving that word up there. Let's describe what the system is. You are going to pick two big primes. P and Q. It kind of doesn't matter how you figure them out. You're going to then compute two things. You're going to compute n, which is the product of those two guys. And you'll also compute Well, I don't quite have room to fit it over there. You're also going to want to compute Euler's phi function of n, which is phi of p times phi of q, because of the multiplicativeness of the phi function. And that's p minus 1 times q minus 1, right? Because they're primes. So you've got n and you've got phi of n. Finally, well, not finally, but as far as getting the public information is concerned, finally, you're going to choose an exponent. Most of the time, choosing e equals 3 will do the job. It's like everybody's favorite exponent, and it seems to not matter what you choose for e. That's a little weird, but it seems to be the case that it doesn't even matter what you choose for e. But there is one condition you need to satisfy, which we've seen a couple of times before. You need e to be relatively prime to phi of n. That GCD should be 1. So this is it. You keep secret what the P and Q are. You compute their product. You also compute the phi of their product. And that's mostly just so that you can do this verification. What you're going to publish and tell the whole world is n and e. Actually, we'll write it as a pair, n comma e. That's your public key. So the idea is that you've given people a way to encode something and send it to you. But that encoded something is garbage to anybody but you. That's the idea. Okay, so we're going to need, for us, with our secret knowledge of what the primes are, to be able to reverse the process and figure out what the message is. I guess... I wish I could go continue at the bottom, but I've run out of space. But there's one more step here. What anyone can do. If they want to send something to me, let's call it message, or let's just abbreviate it, MSG. And it sounds like monosodium glutamate, and I wrote a Q instead of a G anyway. MSG. What they're going to do is raise MSG to the e. Right? The reason I use the letter e is because it's an exponent, modulo n. Of course, when somebody sends some crazy encrypted thing to me, it's quite possible there are eavesdroppers listening in on the line. When a packet goes down the interwebs, it's routed around by lots and lots of different machines, any one of which could look at it, store it, shunt it off to the side, give it to somebody else. We need it to be just be garbage to anybody else who might look at it. So what am I going to do to decode this message to the e power? Well, here's the deal. For decoding, I know what phi of n is. Right? I know what phi of n is. And as far as anyone can tell, the only way you can figure out what phi of n is to know how n factors. But, that's actually... There's still people trying to figure out ways to deduce what phi of n is from n without having to know its factors. For decoding, though, I can know phi of n. So what I can do is compute an inverse for E modulo phi of n. Let's call it F, but it's E inverse mod, or I think we really need more room for that. F, which is equal to E inverse mod phi of n. So great, what does that do? Well, they sent me a message to the E, and I'm going to raise that to the F mod n. That's message to the EF, right? But that's the same thing. Well, I should probably say congruent because, but in practice we size the message into blocks that are small enough that you never get past the, no, that's not true. It's because the exponents may easily take us out of, yeah, we do need congruence here. Anyway, we're gonna take message to the EF, and that's the same thing because E and F are inverses as message to the 1. So this is a strange situation. Somebody else can raise things to the E power mod n. I've told them what n and E are, but I didn't tell them what phi of n is, and I didn't tell them what p and q are. I've got that secret knowledge which allows me to compute the inverse for E, and so that becomes something that I can use, again, modular exponentiation, to turn the scrambled thing back into the message. As terminology I should use. This is called, when you do message to the E, that's called ciphertext. When you get message just to the 1 power, that's called plain text. So we use modular exponentiation to turn the plain text message into the ciphertext. And then we use modular exponentiation with the inverse that we computed in order to undo the process and bring the ciphertext back into plain text. Well, that's RSA in a nutshell. Let's do an example though, shall we? Because it's a little bit hard to see how this works without doing some examples. I'm going to keep the example really small to begin with. So I'm going to use P is 7 and Q is 11. So the N I would publish would be 77. Now, before I release my public key, I'm going to figure out what phi of n is. Of course, that's not hard. Phi of n is 6 times 10. Right? And then I'm going to choose E so that it is relatively prime to that. Now 6 has a 3 in it. Both of them are even. That's got a 3 and that's got a 5. So I can tell you what E can be. It can be anything that doesn't have any 3s or 5s or 2s either, but we're generally not going to make it an even E. Well, how about E equals 7? Now, I'm going to publish then my public key. 77 and 7. It seems like a terrible choice for public key. And obviously this example is small enough that nobody would have a hard time factoring in and breaking this whole thing. The problem comes in when these guys are not 1 and 2 digit primes, but they're 100-digit primes. All right, So suppose somebody wanted to send the message 42 to me. Suppose our message was that, 42. To send or to encrypt, what you do is raise 42 to the 7 power mod 77. All right, so I just cheated a little bit and used Sage because I didn't want to actually by hand compute 42 to the 7 power. Although, you know, we've done fast exponentiation before, so we do kind of know how to do it. Anyway, the encrypted version of that is 70. That is 70 is our ciphertext. So I picked up the wrong marker. This one's turning gray. So why did I just put it down amongst the other markers? Okay. Well, now we still have some work to do. The public key was out there. Actually, probably before you published the public key, you would like to do your other work. What do we need to do? We need to find an inverse for 70 modulo phi of n. So to decrypt it, find, let's see how to say it. Well, I'll just write it as 7 inverse mod 60. And it turns out that that is equal to 43. And I think that's a funny coincidence that my message was 42, but the very next number is 7 inverse. Well, whatever. I'm going to take now, if somebody sends me this message 70, I want to see what it says. I'm going to take 70 to the 43rd power. Again, modulo our product of the primes, modulo 77. Well, I'm kind of out of space, but I'm also done. So compute 70 to the 43 mod 77 to decipher. If I write small enough, it just fits. So that's an example of RSA. I think we'll run this on a computer to do a more sizable example. Although, since I went ahead and cheated, we could have. I should have probably done this one on a computer because I was having to raise the 7th power of 42. That's fairly big. Yeah. Okay. Let's try to do a little RSA encryption and decryption with something a little more reasonable, a larger thing. But we won't go overboard here. I think I want P to have maybe 10 digits, Q to have 10 or 11 digits. See how that works out. So we're going to define P to be the next prime after a random 10-digit number, and I'm just going to try to mash the keys up here. Oh, how far did I go? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, 12-digit number. Right? Okay, so there we go. We've got a fairly good size P. Let's do the same thing to get Q. Looks about the same size. Okay, so now I've got two good-sized prime numbers. Let's let n be their product. Sorry, I should have included the part that would make it print out what n is. Oh, wow, see, that's a big number, right? Imagine you were faced with that thing and you were told, it factors into two primes. You want to get started? Okay, it's not even, not divisible by 3, not divisible by 5. You'd be going at that trial division until you reached something like this that had 12 digits in it. And you finally go, oh, there it is, it's divisible by. I guess it would be this one first. You run into the smaller factor, but both factors are gigantic, so you'd be at that for quite a long time. Yeah. We need phi of n. I'm just going to call it phi here because we can say what it is. It's p minus 1 times q minus 1. That is, I don't really need to use the built-in phi function because I know what p and q are. Okay, so phi is a pretty big number here, isn't it? The way this stuff works in practice is most likely, if I pick a small prime number, it's not going to have any factors in common with either p minus 1 or q minus 1. So let's just see. Suppose I picked 3. What is the GCD of 3 and phi? Remember, GCD is something you can compute quickly. Oh, great. Phi does have a 3 in it. All right, so let's not use 3. Should I use 5? Actually, I know from that final 0, I shouldn't use 5. How about 7? Well, left out a comma, didn't I? So I'm somehow in override mode instead of insert mode. There we go. Okay, 7 will work. 7 is relatively prime to phi of n. As I mentioned before, you don't really need to be careful about what the encoding power is, because the secretness is knowing what phi is. All right, so while we're at it, let's go ahead and compute the inverse. I like to call, I think in the board I call them E and F, but I personally like to call them E and D, because E for encoding and D for decoding, or enciphering and deciphering. So D is going to be equal to the modular inverse of 7 mod phi. That is mod 7 comma phi to the minus 1. Oh, sorry. I keep doing the thing where I forget that you need to type the thing again to get it to actually print it out. Wow, it's a big number, right? But that doesn't matter. Again, modular exponentiation is really, really quick. All right. So suppose somebody has a big message that they want to send to me, a message that is smaller than n, so it can be encoded as a number mod n. I'm trying to think of a good number. Let's say, how many digits are in this thing anyway? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 digits. How about I'll just make my message not have quite that many digits, have 23 digits. There you go. That's a 20-digit number, right? And that'll be really obvious, right? So we've got message is that if somebody wants to send message to me using my public key, they compute this. Actually, let's do it with the built-in modular arithmetic stuff. Take mod of message and n, the modular value, or the number message converted into a mod n value. In other words, thought of as a Karnaugh class. And we will raise that to the 7 power. That was our encoding exponent. We should call this something. Well, message, how about we'll call it cipher, because that's what it is, the enciphered version of our message. And I forgot to print cipher. Well, there it is. It's some giant number. It's a number mod n, so it's not exceeding that 24-digit number, but it is big. Well, now we're ready to decrypt. Somebody has raised message to the 7 power, and they've sent it to us. Nobody else on Earth has the secret information we have, so they would be able to figure this out. But we can take cipher and raise it to the, what do I call it? Did I name it D? I did name it D. Cipher to the D power. Wow, just that quick. 1, 2, 3, 4, 5, 6, 7, 8, 9. Did you think cipher to the D power was going to take a while? Because it's like a 20-something digit number, and D was a 24-digit number again. I'm surprised. I hope you are too. That, again, the modular exponentiation, very, very fast. And you see that raising to the E power made it incomprehensible, but then raising back to the D power brought it back. That's the idea. All right, well, that'll be it for today. So hopefully I'll get this posted. It's 10 p.m. now, so it's going to be a little bit on the late side. Hopefully you'll be able to get a look at it during the day